last week's lecture, we were talking about concepts such as the geoid, the ellipsoid, and the datum. Well, we have talked about how Earth is a three-dimensional surface, and for a GIS analysis, we need to represent that three-dimensional surface on a flat map. So we use projection to do the conversion from the Earth to a geoid to an ellipsoid to a datum and then to a flat map now. So it is not possible to represent Earth's surface on a flat map without introducing distortion. And for this example, a common example to use is an orange. An orange again is similar to a sphere. And if you peel that orange and try to flatten the peel, again, we're going to see some stretches and tearing just to flatten that orange peel. And the same is true for the Earth. So for methods for depicting the 3D Earth on a flat surface, it's specified by these bullet points here. So again, there are three types of projection surfaces. For example, we have a conic surface projection, a planar surface projection, and a cylindrical projection surface, which we'll get into in the next few slides. Also, tangency or case of the projection surface, and also we're looking at the orientation of the projection surface. So there are many map projections, and these map projections are simply created to capture the best information with the least distortion. So these are our three projection surfaces and the two types of case. So our first type of projection surface is the conic projection surface, and we can see here that for a tangent case, let me get my pencil or marker to go to draw. So for a tangent case for conic, it will show one standard line. Oh, I was trying to draw on it, but I don't know if it's okay. So now it is letting me draw on it. So we have one standard line or a line of contact with between the projection surface and the Earth. Whereas for a second case, you'll have two lines of contact with the conic projection surface and the Earth. So again, for the cylindrical projection surface, you have the cylindrical surface wrapping around the Earth, and again we have one line of contact. We have one line of contact, which is a tangent case, and then we have two lines of contact, which is a secant case. And then for a planar, we have one point of contact rather than a line of contact for the tangent case, and then for the secant case, you'll have one line of contact. So again, these are three projection surfaces and the two types of case. So tangent is one line of contact or one point of contact, and then secant case is two lines of contact. Or for planar, it will be considered as one line of contact. So again, for the cylindrical projection surface, you have a cylindrical paper wrapping around a transparent globe or Earth, and inside the Earth there is a light bulb, and this light bulb is projecting the latitude and longitude grids on the cylindrical surface. So again, we have our longitude lines and our latitude lines being projected onto the cylindrical surface, and you will sketch out those latitude and longitude lines from the transparent globe that has the light in it, and then you unwrap the projection surface and you get this type of map. And this is how the latitude and longitude grid lines look on a flat surface map. An example of a cylindrical projection is the Mercator. Again, for the tangency for the cylindrical projection surface, you have one standard line, and we could say that this one standard line is found along the equator. So again, this one line of contact is also known as a standard line. And this could be an example of the equator. And then we could see here in this example, this is a secant because we have two standard lines, or two lines of contact between the projection surface and the Earth. So the map is true to scale only around that standard line. So here in this area, the map is true to scale, meaning that there are no distortions of that area over here where the projection surface is touching the Earth's surface. And again, there are three different aspects, but here in this slide we are seeing transverse, which is normal rotated by 90 degrees, and then we have oblique, which is at an angle. Again, here we have normal, transverse, and oblique. So you can see that the orientation of the cylinder is different. And what's the purpose of doing all this projection? Well, it is to capture different types of Earth's surface accurately. For example, for United States, if I were to draw United States, United States has a north to south extent, and it also has an east to west extent. So north, east, south, west. And again, if we're talking about Japan, Japan consists of small islands. Japan has a north to south extent. It doesn't really have an east to west extent. So for Japan, an oblique projection would be great, or a better fit than a normal or transverse projection, because that oblique standard line, like we see here, is cutting across the middle of Japan. And for United States, we would say a normal or transverse would be better for the cylindrical projection. And then this is an example of a conic projection surface. And for a conic projection surface, we can see here that you have the conic projection surface wrapping around the transparent globe, and when you project the latitude and longitude lines, we see that it's projected like this on a flat map, and we could see that it has a dip. And again, for conic surface projections, there you could either have a tangent case or a secant case. And for the tangent case, we could see there is one standard line, and this is the point of a line of contact between the projection surface and the Earth. And then you have two standard lines in this example. So in a second case, the conical projections are great for countries such as the United States, which has both the north to south extent and the east to west extent. So this could be the United States, and again it fits that the United States accurately. And again, we could see that there are different aspects for the conic. You could either have normal, and then in this case, this is a tangent normal conic projection, or you could have a transverse conic projection or an oblique conic projection. The point is we want the standard line to cut across a specific area and find an orientation of the region that we want to depict. So again, is this example secant or tangent? And is it normal, transverse, or oblique? Well, again, we see two standard lines. So this is secant, and it's a normal projection, normal conic projection. And then here they have it labeled as a central meridian and two standard parallels. Most United States maps are represented using some kind of a secant conic projection so that you can capture least distortion in that mapping process. And this map projection is great for United States, but this secant conic projection may not be great for, let's say, Argentina or Peru, which has a north to south orientation. And we have also the planar projection surface, also known as azimuthal. And here you could see that this is a surface where a flat surface is applied on the top. So you usually have one point of contact, and this is an example of how it looks on a map. And again, for tangency, we have a standard point right here or a standard line. So tangent, it's a standard point, whereas for secant, it's a standard line. So you get a more accurate map for a larger region of the poles. Whereas for the standard point, it is a smaller area that you're showing a true accuracy for on that map. So again, planar projections are great for depicting polar areas or smaller island nations. Now, planar projections can be oblique, normal, or in an angle. It depends on what part of the world we want to show. For example, if we are showing a polar area, like right here, a normal orientation is great, but if we want to show our island in one particular point, we can use the oblique aspect, or we can change the orientation of that plane into that location where we want to map that area to reduce distortion. And then we can see this is how it would look on a map.